So let's continue with the second talk by Zachary.
Yeah.
Okay. Thank you.
I'm going to talk about how to do closure conversion in little pieces. This is joint work with Paul Downen and Zena, Ariola. So passing and returning unevaluated code is possible in many languages. For instance, in OCaml, we can pass functions, and in this case, the x plus y would be the unevaluated code that's passed at runtime. We can also do things like this in Haskell, where x will remain unevaluated, and it contains the code for 20 plus y. So the question is, how are these delayed expressions implemented? Well, one option is environment abstract machines, and I'm glad we just had that talk right there. Variables are placed in the local environment for later. So if we look at the Krivine machine, we have three parts. We have first an environment, which I call sigma, and then we have an expression, in this case an application, and a call stack, k. In the case of this application, we're going to push a closure on the call stack, which captures the whole environment that n needs to execute. When we see a lambda, we're going to grab that closure that's on the call stack, put it in the local environment, and then jump into the body of the lambda. And when we see a variable, we're going to look up the variable in the local environment, we'll see a closure there, and then we'll enter the closure. So anywhere code is delayed and will be passed as a variable, we must use a closure. So I gave the example of the Krivine machine, but the SECD machine, the Zinc machine, CEK, are other machines that will use this delayed environment, and they are strict languages, so they will only have closures around functions. The Krivine machines for call by name. The point of these environment abstract machines, or what they do with closures, is capture them in the runtime. That's in contrast to another option for implementation, which is to compile away closures. And we'll use a transformation called closure conversion, wherein we first pick a target language that has a strict semantics, products, and functions. C's a common example of a portable assembler. Next, we're going to generate code for the delayed substitutions. So in this OCaml example from earlier, which is a function from int, we're going to compile the code to an existential package where it hides a pair, and the first argument of the pair is a representation of the free variables that are needed to compute. And then the second part is a first order function which will know how to break apart the environment and reinstantiate it in the code. For all the applications in our program, we're going to need to generate code to unpack this existential pair. And then, so we unpack it, and we bind the environment inside and then the new function, and then we apply the new function to the environment in the formal parameter. So what is the compiler architecture we get with closure conversion is we'll have a source language, and we'll compile to some intermediate language where we might do optimizations. And then code generation includes this closure conversion step. So if we wanted to have a different closure conversion, one that does optimizations, for instance, it would be a different code generation phase or transformation. If we want to prove correctness for different closure conversions, we also have to construct different cross-language logical relations for each of them. And another thing is that if we want to do closure-aware optimizations, we can only sort of do them implicitly. If you've read compiling with continuations, for example, there's transformations which lift code up to put it next to each other so they end up in the same closure once we do code generation, which is nice, but if you wanted to do more optimizations after, you'd have to be careful about clobbering the code you set up. So our goal was to compile with the closures instead of optimize after. So we want this compiler architecture where we do optimizations and closure conversion together. So we could interleave closure conversions and other optimizations. And code generation becomes simpler. This isn't an unheard of design. Things like unboxed types were sort of an inspiration, where those were something that were done during code generation, but once you brought it up to the intermediate language in Haskell, you could do an unboxed type transformation and then have different boxings fuse away because of other optimizations interacting with it. So what needs to be true for such a thing to be possible is that closure conversion needs to be an equality in our intermediate language. More specifically, this sort of equation needs to hold where M is equivalent to the closure conversion of M. So why can we not just do this with the closure conversion I presented before? Well, it's because this isn't true. Closure conversions change the type. We already saw this, but we turned an int-to-int into an existential type, and equational theories are often type preserving, so this is a problem. Another problem is that it's a global transformation, whereas equational theories are local transformations. And just as evidence for that, for every application, we had to generate this code to unpack our closure. Another problem with it is it doesn't commute with substitution. So if it did commute, we'd be able to closure convert and then apply substitution, and that should be equivalent to applying the substitution, then do closure conversion.
At least not.
It doesn't. Here's a nice little counter proof for that, is that if we just have lambda x, z dot x, so we have one free variable, and this is the thing that would need to be true. Well, if we closure convert first, then we'll have x as a free variable in the closure. If we closure convert second, after doing substitution, substitution would eliminate x from the free variables. So we'd get a closure with an empty environment. And that is not true because the product with one thing in it is not equal to the product with nothing in it. And because it doesn't commute with substitution, beta laws are not preserved by closure conversion, or laws that involve substitution. Here's another problem, is that for non-strict languages, the target of closure conversion is a strict language. And to demonstrate that, here's sort of a hand-wavy closure conversion for call by name. So we saw with the Curvine machine that we need closures for function arguments. In this case, this let expression needs to be strict if in our C-like semantics, we're going to actually look up the variables, the free variables y0 through yn at runtime before constructing an object. The story is even worse for memoizing languages where the target ends up needing mutation because you evaluate the closure at most once. So you need to have mutation in your closure conversion transformation. So what's the solution to all these problems? It's to use abstract closures. These are special laws that, or special objects where we have a delayed substitution in the code that uses the delayed substitution. And we're going to create special laws that understand the relationship between those two parts. So if we were to abstract closure convert the OCaml code, we'd have this thing which looks very similar to what we had before, where we have an identity substitution for y and a function. But there's a difference, is that we have the same type, which is nice. And we can have the same type because the elimination form for abstract closures doesn't change. So we also avoid the go everywhere and replace all the call sites. And we have a new beta law for abstract closures where when we do an application, we're going to take the delayed substitution and the formal parameter and jump into the code with that whole substitution together. This in contrast to the old beta law. So using abstract closures, we don't change the type. It's local, defined with a new beta law, and the elimination form does not change. It commutes with substitution, and it's good for non-strict languages because we can specify laws instead of change the target language. So what do we have in the paper is that we formalize these ideas and call by push value. The main reason was that I didn't want to do the work multiple times for call by name and call by value, and call by push value is good for that. It's also an interesting new language to see what closure conversion is like because there isn't work on that yet. And it has a bonus of being good for reasoning about multi-arity function closures. So in the paper we present something like this, where the transformations from call by name and call by value into call by push value were already published by Levy. So where do we put closures in call by push value? A little call by push value primer for us. It's divided into two syntactic categories, one for computations, which we have in orangish red, and values, or greenish blue. Computations are things that can be evaluated. So we have functions, applications, returning values, and forcing thunks. And values are things that don't require any, or they can't reduce. They already are. And this includes variables, values of base types, and thunks. And to go between values and computations, we have F and U, which are shifts between the syntactic categories. Where do we put closures in such a language? Well, consider two facts, that beta laws only relate to computations, and only values can be substituted. And I mentioned earlier that we use closures to capture the delayed substitutions of things that might appear in a different environment later. So in call by push value, because of the shifts, we always want to, or we have to rather, by the syntax, we have to go through a thunk in order to pass a computation to another part of the program. So that is the place where we need to put closures for call by push value. And what do we need to add? We have what I call an environment, but it's essentially the same syntax as a substitution. And we have a new value, which is a abstract closure for a delayed computation. How do we type check these things? Well, the environment will generate an environment extension that we provide to the delayed computation. And something to notice here is that M is covered by gamma and gamma prime, so we don't require that it's completely closed, which is important, we'll see later. And we need a new law for beta, which is when we force a delayed expression, we're also going to apply the delayed substitution. And all the other laws for call by push value are changed. So that's how we add abstract closures to call by push value. What can we do with it? Well, the topic of the paper was closure conversion in little pieces. So we can do a transformation where we add one free variable at a time, and this will make up closure conversion. This is the transformation where on the left-hand side we have a delayed, an abstract closure. We see there's a free variable missing from it, and we just add an identity substitution to the closure. And then a naive closure conversion, which corresponds to flat closures, will just be the normal form with respect to this rewrite rule. And this is why we need abstract closures to be partial. So if you convert from call by value into call by push value, you don't have any closures in the program, then you'll have a bunch of empty abstract closures there. So they won't close over M, and you're just going to add one variable at a time until all the abstract closures have captured their whole environment. This rewrite rule is an equality in our theory. So if we start with the left-hand side of the rule, and then we perform an identity substitution on M, this identity substitution contains all the variables which were previously in sigma with the addition of y. And then we do a beta expansion followed by an eta reduction, and then perform the final substitution. We end up with a closure with one more variable. So we can also do other things with the abstract closures. An example is the optimization of lambda lifting, which will take a variable that was passed in a closure and it'll place it on the call stack. So you're trading heap space for stack space, and stack space is often faster. So we'll start with an already closure converted program, which has the free variable in. And notice that in the body of this let expression, we can see the binding for X. I'm not going to go through all the steps here, but it involves a bunch of beta retractions and expansions. And when we get to the end here, what do we have? We transform the body of the closure to a lambda that's going to pull in off the stack instead. And then at the call site, we added in as an extra argument. And so in is now passed on the stack instead of being part of a closure. What can we say about the correctness of closure conversions with abstract closures? Well, I just showed you proofs verifying that closure conversion and lambda lifting are correct in our equational theory, and it's just give a derivation in the theory. And these composed by the transitivity of our equational theory. And there was no need for cross-language logical relations, which are the common approach for proving the correctness of closure conversions. All that matters is that our equational theory is sound. So soundness is defined as if you have an equation, then the two expressions must be equivalent in the operational semantics. And we define our operational semantics over an abstract machine, an environment abstract machine. We also have another theorem in the paper called adequacy, which I have an informal description of it here, but the essence of it is to say that when you've performed closure conversion, that you can run on a simpler machine. So if you have a completely unclosure converted program, you need an abstract machine which will capture the closures at runtime. But after closure conversion, you treat the abstract closures more as products, where you're just going in and you're substituting in those free variables. And there's a performance advantage too, where a naive machine with no closure conversion will have to capture the whole environment because it doesn't know anything about the code unless it traverses the code for free variables, but that would be very slow. So we save on space by doing the closure conversion. To wrap things up, what we'd go for. So we did closure conversion in the intermediate language using abstract closures in a step-by-step incremental fashion. Call by push value was a nice place to do it because it has one spot where we need to capture closures. For call by name and call by value, there were two different spots, if you looked at them, for capturing closures. Common closure conversion optimizations are now just compositions of beta and eta laws within our language. And we also can simplify the proofs of closure conversion correctness by just having different derivations in our language. There's more in the paper that felt like too much to get into for the talk. Is we present environment-based abstract machines for call by push value, which were very similar. They're an extension to Levy's CK machine for call by push value with a delayed environment. Another thing we do is that we wanted to handle sharing too, because those closures behave a little differently than those in call by value and call by name. So we extended call by push value with a sharing part, which sort of sits in between computations and values. We call them shared computations. And we can actually compile call by need into it and preserve the full equational theory of call by need, including extensionality laws. And then we add closures to that thing as well. So I lied at the beginning. This is what we actually have in the paper, is this language. So if I could leave you with, the main point of the paper is that closure conversion is an equality, a syntactic equality, that is. Yeah, I'm done. Sorry.
That's a very nice talk, very cute. I have so many questions, but I'll just ask a couple. So does it extend to polymorphism? Can you do?
No, that would be future work. Polymorphism and recursion are things that I set out as future work. Yeah. So.
Okay, and so you had a theorem called adequacy. So does that name suggest it's the adequacy theorem in a technical?
No, so what people use adequacy for closure conversion, more to say it does something, but other people tend to use adequacy to say that it's like the fundamental theorem of a logical relation. But we have a theorem like that too, I just call it something different.
Okay.
Sorry.
Right, one final. Can you do kind of optimizations of like sharing of environments or nesting of environments?
Yeah, so the two examples we have in the paper are that lambda lifting one and then the environment sharing example that Appel uses in all his papers. So both of those are very capable. I'm not going to claim that all closure optimizations can be done in this system, but at least those two can.
Great talk. I was wondering if you are aware of contextual modal type theory.
No, I'm not.
Because it's pretty similar. You use the box to create like code, and then but you can actually put like variables, dynamic variables within the code. So it looks like a closure.
That's very
pretty similar. It reminded me.
Contextual modal type theory.
Yeah.
Okay, I'll look into it. Thank you.
Hello, yeah. It's going to sound critical, but it's not. You draw attention to the fact that closure conversion doesn't commute with substitution.
Yeah.
And I wonder why I should care. I don't usually expect my optimizations or my transformations to commute with substitution.
Well, it's so if we want the equational theory to be sound, one that includes closure conversion as a transformation, it needs to preserve the beta laws. So if you had m equals n, it should be the case that, well, in that beta law, so lambda x, m applied to v equals m.
Oh yeah, that's just for the locality problem. It's the same,
Yeah,
it's the same problem as that.
It's a problem with the soundness of the equational theory. You can't
Yeah.
prove it if
Yes,
it
you-
doesn't commute with substitution. So the reason people use logical relations to prove the correctness is because you step outside of the syntactic theory and you can prove things are correct. I mean, people closure convert and things run correctly anyways. But if you want to have a sound equational theory, it's hard to do it without commuting with substitution.
Right. I think of it as a compiler writer, and in GHC, the way you work around that is by making these wrappers. So you just you do the transformation locally, you pack it around a function typically, or something that has the original type,
Yeah.
and that will be inlined and will be transformed.
So the worker wrapper thing scares me specifically for this problem because, closures are about functions and code, and how are you going to do closure conversion where you can introduce more high order functions to do it?
I mean, absolutely.
So that was my worry with that.
I
I actually, in an earlier paper, I talked about doing worker wrappers to introduce closures locally. But you also run into a problem where, for Haskell in particular, that closure conversion ends up introducing mutation and so
Yeah.
changing the...
Absolutely.
Yeah.
Thanks.
Thank you.
Can you say a little bit more about this extension of call by push value being able to encode call by need?
Yeah, so this isn't the first work that tries to do there. There's extended call by push value, which was like in 2018. What they did there was they added computation variables, and all of the shared stuff was hid between an F type. What we didn't like about that work is that it didn't preserve the extensionality principles of call by need. So if you saw in the proofs, we used Ada a lot. So we needed that, and we extended it by adding shared computations, which can reduce into shared variables. So we sort of, Levy's like, oh, computations are and values do. We sort of pervert that idea and add in shared computations and shared values, and we have shifts for those in between. So for shared computations, we have a shift to computations and a shift to values as well. So there's other work beyond polarity, which was Paul Downen and Zena as well, which is sort of a similar idea where you have 3 different kinds of types and then shifts in between them. And that's how you can preserve all the equational theory of call by push value, but then add in this extra sharing thing. So it's a conservative extension to call by push value. We didn't have to change any of the laws, which was nice.
Thank
We
you.
can talk more offline if you want to. So
Thank you very much. Okay, let's move to the